Thanks, Kyle. Very nice talk on manipulating hair in face images. In the next 20 minutes, I would like to switch the focus from hair to the whole portrait and discuss creative face stylization for images and beyond. First of all, a brief introduction of face stylization. Given the target face image and a single style reference, we want to extract the style representation from the reference and apply it onto the content of the target, which preserves the face structure and identity. And output should have visual similarity to the reference. The reference could be an arbitrary image or another face image to make better use of the facial semantic information. Let's start from the very first neural style transfer method, where Gattis and colleagues proposed a parametric method that does optimization to statistically match style and content features. This method applies to arbitrary styles, but it is not perfect regarding both quality and speed. Therefore, lots of works have been done to improve this baseline for both general style transfer and face stylization. Here we roughly categorize them into three axes. First of all, better representations of style and content help improve style separation, understanding, and synthesis. Second, using semantic correspondence help achieve more meaningful local stylization. Finally, given that optimization-based methods are usually pretty slow, feed-forward methods are developed to improve the stylization efficiency to allow real-time applications. Here we discuss some representative works. Regarding representation, this optimization-based style transfer work improves the style content representations with better loss functions to achieve better stylization. Although not directly targeted at stylization, this swapping autoencoder work achieves promising content style encoding with different representations and discriminators on patchwise statistics. Using semantics information, this deep image analogy work represents a non-parametric method that uses dense semantic correspondence to progressively synthesize the result in a cost-to-find manner. And specifically for face, this method uses face prior to perform semantics-aware patch synthesis to achieve nice stylization results. To improve the speed, this add-in method uses conditional normalization to apply the style with a single feed-forward network on arbitrary styles. And more recently, we have a paper that does instant face stylization with approximated facial correspondence and fast pixel lockup. Okay, now that there are so many great progress on face image stylization, can we go beyond image stylization to allow more creative tasks? Today I want to discuss three instances. First of all, by extending image stylization to video, the target is to achieve smooth and consistent video results using the temporal information. Then, stylizing pixel-level appearance is not enough for faces. We also want to capture the geometric styles regarding facial structures. Finally, Besides automatic stylization, it will also be interesting to explore controllable stylization so that user can perform fine-grained control to the results using semantic and spatial manipulation. Let's first discuss video stylization. Most existing work methods focus on achieving temporal smoothness and using image stylization framework on individual frames. Here are some representative works. Actually, besides temporal smoothness, there are many other things can be done on videos. Recently, we collaborated with Czech Technical University and proposed a method for video stylization that allows interactive artistic control. The key questions we want to answer in this project are how to achieve high-fidelity style details, and how to enable instant stylization, feedback for users to iteratively refine. Our solution is to use keyframes as references that are interactively created online and represent styles in patches for effective synthesis. Also, we propose a fast online fine-tuning pipeline for faster style updating. The overall pipeline is very simple, just a patch-level autoencoder structure. Basically, we chop reference frames into small image patches and have the network to learn the style that translate the patches. Patch-wise losses are used to match patch statistics. During the inference time, the same encoder-decoder structure is applied on patches from every individual frame to do the stylization. However, this patch-wise inference can cause temporal flickering because two similar input patches could be mapped to different stylized results. Although GAN losses could help reduce the ambiguity to some extent, but it will still introduce temporal inconsistency. We resolve this issue by introducing an additional positional encoding to provide more information for the convolutional networks to better distinguish different locations. Specifically, we use multi-level Gaussian mixture layers to get dynamic encoding, which is smooth on the temporal axis, and move with motions in the video sequence. The whole training pipeline is within a hyperparameter tuning framework, so fine-tuning could be optimized to achieve the best speed with the optimal parameters, including patch size, network structures, and learning parameters. Here is a video of our setup and interaction steps. We have a camera set up to capture live user painting. User picks a keyframe at a time to stylize. The results are propagated to the whole video with online training and inference. User can add additional keyframes to handle frames with large rotation or deformation. Alright, let's now switch to shape stylization. First of all, why shape stylization is important? The key problems are that Shape deformation is quite important to completely describe a non-photorealistic face style. But current appearance stylization approaches cannot handle these shape changes well. Therefore, we need more explicit ways to handle shape stylization. There are quite a few papers focused on shape stylization. Most of these papers are for 2D facial geometries, such as Kerrigan, The Face of Art, and Wolfgang. But 2D shape is often not enough for various applications. So the question is, can we do 3D shape stylization for complete face reconstruction plus stylization? One of our recent works explored this direction, collaborating with City University of Hong Kong. In this work, we tried to combine 3D shape and appearance stylization into a single framework, with the shape represented by parametric morpho model, and appearance unfolded in the canonical UV space. In our pipeline, we first train a key point translation network, which uses a set of 2D facial key points to perform coarse-level geometric deformation to capture the geometric style in the reference. In this landmark translation network, we ask the network to separate shape, style, and the facial structure to only encode the style of the reference so that the translated key points combine the identity from the target with the geometric style from the style reference. Then, the translated key points are used to deform the 3D parametric face geometry to get the dense shape. The deformation is achieved through optimization of mesh vertices to reflect the key point constraint and also preserve the original mesh structure and details represented by local mesh descriptors. Finally, we use a joint optimization framework based on differentiable render to optimize texture and geometry with multi-view constraints. Basically, we optimize mesh geometry and texture in the UV space so that randomly sampled views rendered with the face model matches the style representation of the reference. Please refer to our paper for more technical details. This framework can handle joint geometry and texture stylization with a single reference, and output could be used in various applications from images to 3D animation. The joint optimization framework also allows control over how much stylization is preferred for geometry or texture. We can use these techniques to drive 3D animation with identity preserved from the input face. Okay, in the last part of my talk, I would like to discuss controllable face stylization. Because instead of fully automatic pipelines, controlled stylization is preferred for providing user with different level of controls. Currently, such control is realized as interpolation factors between styles or ways to control how much style is wanted, or more local controls with key points or masks for annotating sparse correspondences. Or with some semantic attributes so user can change some semantic factors. To add another level of controllability, we explore style manipulation with parametric 3D guidance. In this work, we propose a latent manipulation method that allows stylized face image manipulation with 3D MM attributes. With our disentangle latent to 3D MM parameter mapping, this method enables disentangle and precise control over all 3D MM attributes, including shape, expression, pose, lighting, and albedo. Because 3D MM is usually built on real human faces, we also propose a cross-domain latent matching approach that could manipulate stylized face with real human-based 3D MM. The overall pipeline is shown here. Given one stylized face image, we use cross-domain latent inversion to project it to human face domain and predict 3D MM attributes. These 3D MM attributes can be edited and mapped back to the original style space to generate the final editing results. In more details, our pipeline follows the mutual latent and 3D MM mapping mechanism proposed in StyleRig, but with changes to have better disentanglement between attributes and allow cross-domain mapping. Given the input stylized image, we first use scan inversion to project it to a disentangled latent space with each attribute corresponding to a sub-latent space. An attribute prediction network T is then used to estimate 3D MM parameters across domains. After user perform the manipulation to the 3D MM parameters, the differences of the editing are injected to the latent encoder-decoder network E and D to update the latent code to reflect the manipulation. And finally, the updated latent code is used to generate the image through the pre-trained StyleGAN generator. Please refer to the papers for the implementation details. With our method, we can control stylized face images with semantic 3D controls, which achieves more precise results due to its explicit 3D proxies compared to simple binary attributes. Here are some more results on manipulating face paintings. Okay, that concludes my part today. Basically, we introduced 3 specific creative face stylization problems besides image style transfer, and review some recent works, including our exploration. Thanks for watching, and next, Kyle will talk about object manipulation with volumetric implicit representation.